Hello everyone. In this lecture, we are going to discuss about liquid systems. In the liquid system, what is the dynamics of liquid system? And we have different version of liquid systems like interacting and non-interacting, and how to discuss the dynamics or how to derive the mathematical model for that uh, interacting systems and non-interacting systems. And finally, we'll make one control system for the liquid system. So these are the topics we are going to see in this lecture. Okay, first we'll see what is dynamics. For example, take this tank. So in this tank, actually Q is the normal input and H is the, for that Q, this is the level of the tank. And then for this H, this is the outflow rate. So if there is no change in the inflow, if there is no change in the outflow, if there's no change in the level, means the system is in static condition. But if I want to increase the flow rate from Q to Qi, I have just added a little amount of this. Automatically, the level changes, which is changed by small h. And as a result, the output flow rate will also be changing. So this is called as dynamics. That is, I'm moving from static condition to dynamic condition by introducing a flow rate. So if you do this, so what are the changes? So this dynamics introduces some changes. So in order to understand the dynamics, we always familiar with the term resistance and capacitance. So we are going to see what is the resistance for this change. So if there is a change, what is the resistance offered by the liquid system to challenge that. So for that, the resistance is equivalent to the change in flow rate and the change in the ratio between the change in flow rate and the change in level difference. Like actually, we all know that the familiar system is resistance electrical system V equal to IR, R equal to V by I. So I is the current flow, V is the voltage potential. Similarly here, the flow rate, the current is mapped with the flow rate. So change in current, here also change in flow rate. And then for this change in flow rate, how much is the change in level? Here, how much is the change in potential? So here, suppose for example, here is the resistance. So here V1 and V2, and then here is the current. So R equal to V by I. Similarly here. So here, for example, the resistance, this is the resistance we used to say. So here the level is the change in level, sorry. So here the change in flow rate. So change in flow rate. So here is the flow rate, and then how much level is move changed to this thing. So that is offered by resistance. So resistance equal to change in level divided by change in flow rate. And in terms of units, change in level means it's a height. So meter by flow rate is meter cube per second. So from that we can derive the resistance unit is second by meter square. So the unit for resistance is second by meter square. Okay. Then there are two types of flow. One is laminar flow, another one is turbulent flow. Laminar flow means if the Reynolds number is less than 2000, then that is called as laminar flow. And then the turbulent flow means if the Reynolds number is greater than 2000, then that is called as turbulent flow. So which we can see under the mostly the seawater waves. So this is we can see normal. I mean in our in normal case the laminar flow occurs. So generally flow rate is proportional to the level of the tank level. Okay, so in order to remove the proportionality, we introduce a constant K. So now what is K, what is Q? Steady state liquid flow rate, the unit is given, and then K is the coefficient, because in order to adjust this is the unit given to K, so meter square by second, and this is the steady state. So from this we are going to derive what is the resistance value. So here because this is change in flow rate and change in this. So if you differentiate this, you will get dq equal to k is a constant into dh. And then for resistance, I need dh by dq. So dh by dq is equal to 1 by k. So from this, what is k? K equivalent to q by h. So substitute here in the place of this is k, in the place of k you substitute q by h. So that is h by k. So for laminar flow, this is the resistance. Similarly, for turbulent flow, turbulent flow is proportional to square root of the level. So in order to remove the proportionality, we introduce k. So k is q by root h. Similarly, here also r equal to dh by dq, change in level by change in flow rate. So if you take the differentiative of this derivation of this same expression, dq equal to, this is square root, so 1 by 2 k into h power 1 by 2 minus 1, so which is k into h power minus 1 by 2. So dq equal to k by 2 into root h into dh. Okay. And then we need dh by dq. So if you bring this side, then you'll have 2 root h by k. K is already q by root h. So if you substitute, you will get this. So this is the laminar flow. So laminar flow resistance is h by q, and turbulent flow resistance is 2h by q. So now we have got the resistance. Okay. So with that, we'll enter into the modeling. So generally, the modeling is given in terms of this equation, principle of conservation of some S quantity. So thus S could be total mass, or mass of individual components, or total energy or momentum. So in this case, in liquid level system, we used to take total mass. Suppose if you take temperature system, we have to take total energy. So this quantity differs based on the system you take. So here, the liquid level system, we'll take total mass. So now we'll apply mass in this equation. So accumulation of mass within a system. So if you take any system, how much mass is accumulated with respect to time, that is equivalent to flow of mass in the system with respect to time. So how do we say flow of S? So we know that meter cube by, so second, so this is the flow of mass. So I'll tell you in detail in the next slide. Okay, so flow of mass in the system with respect to time minus flow of mass out of the system with respect to time, that is inflow minus outflow, plus amount of is how much mass is generated because of the reaction, how much mass is generated, and then how much mass is consumed by the system. So generally for liquid system, this is not applicable. For temperature system, we can say that the amount of heat generated or amount of heat consumed. But for liquid level system, we have only these kind of parameters. So to do the mathematical modeling, we take the help of this equation, principle of conservation of any quantity. In this case, in liquid level system, we take the quantity as total mass. Why do we need a modeling is because straight away we cannot we cannot spend, or you cannot invest more money on the system and implement it. Before that, we need to do the simulation. To do the simulation, we need a mathematical modeling. Like anything can be written in terms of mathematical expression. So similarly, we are going to write a mathematical expression for this liquid level system. So once it is done, then we can use the simulation software like MATLAB or Python, and from that we can check whether this system works based on our requirement or not. So once it is done, then we'll invest the money, and accordingly we'll purchase, and we'll go for the direct implementation of the system. For that, modeling is important. So to do the modeling, we use principle of conservation of some quantity. In this case, our quantity is total mass. So now we'll see how this mass is related with this liquid level system. So we all know that density equal to mass by volume. So in this, because we need mass, so mass equal to density into volume. Okay. So we are going to substitute in this. So what is the equation with respect to time period? So d by dt mass. So mass can be written as density into volume, similar, equal to. So here flow of S, so flow of mass. So mass is this rho, and this Fi can be written as volume by time. So volume by time is equivalent to flow rate. So that is replace Fi minus. Then here flow of S. Flow of S means flow of mass. So that mass can be written as rho into V by T. So rho V is mass, time is this. So this is outflow rate. So finally we can say inflow rate minus outflow rate equal to d by dt of V. So this V can be written as A into dH. V can be written as A into H. Or since it is a very small change, A into dH by dt. So the equation is inflow minus outflow equal to rate of accumulation, which is Fi minus F naught equal to A into dH by dt. And then here I'm going to control the level. So in F naught, we have seen that resistance equal to H by Q. Okay, in this case, I need Q. So if you need Q means bring this Q and bring this R. So H by R. Okay, so your flow rate is derived, or flow rate can be replaced like H by R. So Fi minus H by R equal to A into dH by dt. So from this, I'm going to collect, I'm going to bring all the H terms on one side. So that is why this case. And then so this is simplification, and since we are going to analyze this system, the response of the system for a particular input, Laplace transform is the best tool to analyze the stability. Okay, so for that purpose, we are going to convert this equation into Laplace transform. So we all know that. So Fi of S, Fi is changed into Fi of S. This is a constant, and then since it is first derivative, you have to put one term S term and then collect everything on one side. So finally, we are going to get the transfer function. So what is transfer function? Laplace transform of output. So here the output is the level, okay, divided by Laplace transform of input. Input is the inflow rate. So from that we derive this. So RA. So what is RA? RA is resistance, and the A is the area. For example, already we know that the unit is second by meter square for resistance, and then this is meter square. So meter square meter will get cancelled, so we'll get second. That is why whenever you multiply resistance into area, which gives tau, time constant. So time constant equal to RA. So here I have proved. And then here this area is considered as capacitance. So what is capacitance? We'll see. Okay. So let's take an example. So before that, your capacitance is equivalent to change in liquid stored with respect to change in head. So in liquid level system, the area is considered as capacitance of the system. Okay. So now with this ideas, with this resistance and capacitance and the mathematical modeling of a single tank, let us do one simple problem. Okay. So in this problem, a tank. Okay, your tank is taken, and then the tank tau is the time constant is 1 minute. So tau is 1 minute, and then the resistance is 1 by 9 is given, and then this is operating under steady state with the inlet flow of. So inlet flow is 10 feet cube per minute. Then at time t equal to 0. So here let us take at time. This is the time t equal to 0. At time t equal to 0, the flow is, so initially it was 10. So from this it is 10 only. Then when t equal to 0, the flow is suddenly increased. Flow is suddenly increased to, so this is 100 feet cube per minute. So it moved from 10 to 100 at what time? T equal to 0. And it remains there for zero point 0.1 minute. From 0 to zero point 0.1, the level was maintained at this state. So at t equal to 0, the flow is suddenly increased to 100 feet cube for zero point 0.1 minute by adding 9 feet cube of water to the tank uniformly over the period of time 0.1 minute. So plot the response. Okay, so since it is a single tank, we know that the transfer function for a single tank is R by tau s plus 1. Then substitute, then now we have the system. So now we have to analyze the inflow, because there is a change, there is a dynamics in the inflow rate. Okay, so we can take this equation, because Q of t, the difference is 90, and then U of t is this one. This one is U of t, and then this one is t equal to 0.1. So in this U of t, if you subtract this, you will get this point. So that's what given over here. U of t minus U of t minus 0.1. Then you take Laplace transform for this, and this is your H of s divided by Fi of s is already given. And then we need to bring this Fi of s, because we need to calculate H of s. So for that, Fi of s is given over here. Then uh, we can bring this s plus 1 into this, and then take inverse Laplace transform. Then this value, if you find, partial fraction, if you apply, you'll get a equal to 1, b equal to minus 1, then substitute, and then we'll get this equation for 1 by s into s plus 1. Then substitute that. Okay, so when the time is less than zero point 0.1, then this is the equation, because you have to apply this 10, then this. And then when the time is greater than zero point 0.1, which means, so here this is 0, this is zero point 0.1. So after this it behaves like this. So this equation, okay. So 10 into 1 minus e power minus t minus, because this is u of t and then this is u of t minus 1. So that is directly written like this. Then from this we have to simplify and get the equation as h of t equal to 1 minus zero point 0.5 e power minus t. Okay. And then this is the pulse input. So this is the transfer function. And then this is 9. So this is how, I mean, this h of t behaves like this. So e power minus t can substitute various values on that. Then this is the response. Okay. So this is how the system responds. So this is one kind of input. This is one impulse input. Okay. Impulse input is, it exists for a particular time. So that is, if you take Laplace transform for that, then it gives just, that's a number. So the number is 9. So this is how we can plot the response for the given situation. Okay. So one more example. So this is the tank, and then you need to derive the transfer function for this. Okay. So for the tank, the area is given, capacitance is given, R2 is given. So here only one inflow but two outflow. So so the formula is inflow minus outflow equal to rate of accumulation. So inflow is Q, this is Q, outflow is, so we know that flow rate is given in terms of H by R. Okay, so H by R1 this side, H by R2. So since it is 2 flow rate, you have to add and subtract from the inflow rate. If you have 3 or 4, we have to do that. Add all the outflow rates and subtract from the inflow rate. Then simplify this. Okay, then we need the equation in terms of H of S. So you can arrange like this. So finally, Q equal to AS into H of S plus this one, H of S by R equivalent, where R equivalent is this one. Okay, if you take the LCM, then we can get one R equivalent. So substitute that. So from this we derive the equation. So H of, because this is a transfer function, Laplace transform of output by Laplace transform of input. So that is R equivalent by A into R equivalent S plus 1. So substitute this, then we'll get the transfer function. So likewise, you can add one more flow rate or one more flow rate. So accordingly, you can derive the equation. So one more system. In this system, this is the inflow. Here also we have two outflows. One is the pump. Pump is constant. Okay. So if you have a resistance on this, it is varying, but this is a pump, which is constant flow rate. And then here, the pipe, the resistance is given, or it is inbuilt, or it is built 0.6 meter above the base of the tank. So you have to calculate this also. So we'll see how it affects the system. Okay. So in the first condition, the tank operates steady state value at H equal to zero point 0.3. So for this case, so when H is equal to zero point 0.3, the outlet is, so see in this, the height is 0.3. 0.3 means here. So if the level is here, the outlet is only through pump. If the level is here, the outlet is through this path and then this path. But first, the first condition is H is equal to 0.3, which is below this pipeline. So the outflow rate is only through this pump. Okay. So Q minus, so in the formula is inflow minus outflow. Inflow is Q, outflow is the pump. Okay, but it is not a varying one, it's a constant. So minus 3 equal to, as usual, A into dH by dt. So if you take a Laplace transform, this will be 0. So Q of S equal to, there's like take a Laplace transform. So AS into H of S. So from this outflow, I mean transfer function is Laplace transform of output by Laplace transform of input. So which is 1 by AS. A is given as 0.1 cross section area. So this is the equation. So suppose if I want to plot the response of this means, so first H of S equal to 1 by 0.1 S into Q of S. So let's say this Q of S equal to a step signal. So for the step signal, the magnitude is 1. For this, the Laplace transform is 1 by S. So we'll substitute. So 1 by 0.1 S square. So this is H of S. Suppose if I take inverse Laplace transform, it is H of t equal to 1 by 0.1 into, which means if I plot, it goes on increasing. So this is H of t. So this system is called as pure capacitance. Capacitance means area. It has only area. So this is called as pure capacitance response. For this system, definitely we have to implement control system because it keeps on moving. We have to bring it to settle at particular level. So we need a control system. So in order to understand whether we have to implement control system or not, this mathematical modeling helps a lot. So in this case, if you have a pump, so from this we can give a statement that if a tank has pump as the outlet. So in that case, we need control system to bring the level to a desired level. Okay. So this is the proof. So in this case, the outlet is through this pump because the level is only at 0.3. So the second case is if the level is at 1 meter, which is above. If the level is at 1 meter, there are two outflow rate. We'll see that. Okay. The first case was discussed, which was the level of the tank when it was zero point 0.3, what is the transfer function? Similarly, so for this case, so here the second case is, okay, so in the second case it is 1 meter. So 1 meter means it has two outlets. One is pump, another one is this pipe. So why we have taken 0.6 means because this is the tank and then the pipeline was constructed above zero point 0.6 meters from the base of the tank. So this whole thing is H. We have to subtract this. We don't need this because from here only this dynamics is actuated. So H minus 0.6. Okay. Then as usual, take Laplace transform. So finally, we'll have this kind of transfer function. Then next problem is flow rate is given. Okay. From this, then two different heads are given. From this, you have to calculate what is tau. So we know that tau formula is R into C. So since this is the flow rate is square root of H, which means it is turbulent flow. Turbulent flow means the R is equal to 2H by Q. So substitute here to 2 into H. So H is given 2 meter and then Q is 0.6 root of H. So just cancel this. So you will get tau equal to 9.43 second when H is equal to 2 and then 14.9 when H is equal to 5. That's it. Okay, so now we'll move to the next level. So far we have seen only single tank and then the single tank dynamics is realized in terms of resistance and capacitance. So resistance is equivalent to H by Q for laminar flow and it is equivalent to 2H by Q for turbulent flow. Then we have seen the transfer function. We have seen some different conditions. On that, we have derived the transfer function. This is one section. The next one is if the tank is connected in this fashion. So what is the transfer function? So here the point is whenever I give resistance to this, automatically two levels will be affected. Whereas in this case, only this one will be affected. Okay, this level directly. So here, whenever I change, directly it affects these two tank levels. So we'll see that how we can bring those changes in the mathematical modeling. So first we'll take one tank. So we all know that in the tank, the mathematical modeling is input minus output. So inflow is Q, outflow is Q1, which is equivalent to the rate of accumulation. So A1 into dH1 by dt. So here Q leave it because in Q1 only we are going to replace by H. So Q1 is affected. I mean, if you change the flow rate, automatically H1 and H2 will be affected. But that is the difference between them only, not the addition. So H1 minus H2 divided by R1 equal to this. Then you have to rearrange. Finally, you take Laplace transform and leave it like this because we are going to do for the second tank as well. Then we have to substitute this. So now what we have done, we have taken one tank, we have implemented the changes, and we have taken Laplace transform, and we are going to do the same for the second tank. Okay, so second tank. So in the second tank, it affects only the second level. Okay, but in Q1 it affects H1 minus H2. Okay, so again here also take Laplace transform, then simplify it, then finally from this your expression is this. So now we have to merge the expression so that I should get H2 by Q, the influent. So I need to, because H2 I should not disturb, but H1 I can replace. Okay. So in the first tank, the equation is this one, Q of S minus S. In the place of H1, replace this H1 so that we will have the equation in terms of H2 and Q alone. So substitute here. First I have substitute this one. So R1, R2. So here this tau 2 is R2, A2. Then R1 by R2, this one. And then here bring this H2S, this H2S. Okay. So Q of S is done. And then this 1 into H2 of S, then this H2 of S will be cancelled. So there is no H2. Then equal to A1 is here. And then H1, we have to substitute this. Okay, so you can cancel the relevant terms. Then this can be tau 2s. So Q of S minus 1 by R tau 2s H2 of S equal to A1 of S, and then you bring this H2 of S in in this place. So bring that, then you can combine the relevant terms. Then finally you will get this kind of transfer function. So H2 by Q equal to R2 by tau 1 tau 2, which is area of so here in this we have R1 C1 R2 C2 like that. So here this alone, and then this says the interaction. So if you take non-interacting, this term is missing. But if you take interacting tank, this is the interaction between the first tank and the interaction between the second tank. So this is very important term. This term decides the interaction. If this is missing, then we can say it is non-interacting. Okay. So now we'll solve this using a block diagram. This is using derivation. How do we derive this equation from the block diagram using block reduction? Before that, we should know what is Q1. Q1 equal to H1. We know that H1 minus H2 by R1. Then Q2 equal to H2 by R2. Then we can implement this in the block diagram. How? H1 of S minus H2 of S, that is divided by R1, which is Q1 of S. Similarly, H2 of S by R2 of S. So H2 of S by R2 gives Q2 of S. Okay. Then Q minus Q1, this is a tank one. So Q minus Q1 equal to A1 dH1 by dt. So if you take Laplace transform, you'll get this. So now we can implement this in the block diagram. So here how Q minus Q1 divided by C1 equal to, that is A1 actually, C1 or C1 same, H1 of S. Then this is for the second tank. So Q1 minus Q2. So from this, see Q1 minus Q2, 1 by C2. So we have taken all the terms separately. Now we are going to combine. So first we need H1 of S. H1 of S means Qi minus Q1 divided by C1 of S. So this is H1 of S. Similarly, we'll take this tank. So in the second tank, it is Q1 minus Q2. So Q1 minus Q2. So here, sorry, Q1 minus Q2 divided by C2. So that is given. That is H2. Okay. So first do this term and then do this term. Then you give the relation between. So here H1. So from here we can get H2. H1 minus H2 equal to, this is the Q1. So similarly here, then we can combine, then apply block reduction algebra, block reduction technique, and then you will get this transfer function. So using block diagrams also we can get this equation. Okay. So on small exercise for you guys, the same thing, but here the derivation is between H and Q. So now you have to do the derivation for output flow rate, not the level. So you can try this. Okay. Next, non-interacting tanks. So can you see the difference? So here non-interacting tanks. So this one will affect, this one will affect, but not this one will not affect both the levels. So it's so simple. So first take tank one. So Q minus Q1. Okay, this output is Q1 equal to A1 into dH1 by dt. So replace this because we need an expression. So H1 by R1, substitute it, and then we'll get this equation. Okay. Similarly, tank 2. So Q1 minus Q0 because output is Q0. So you can substitute what is Q1 and Q2 or Q0, and then from this you'll get this equation. Okay. Yeah, this is the equation. H1 of S by R1 because we need one complete equation. So solve this. So here you have A2 and R2 and H2 of S, and then R2 by H1 of S equal to this one, and then we can substitute this equation here. Okay, so from this h1 of, because we don't need h1 of s, so you have to replace. So h1 of s can be given as r1 by tau 1 of s. So substitute that here, then you will get R2 by this. So the difference between non-interacting is, this term, so this is non-interacting and then this is interacting. The difference between this term is added. Since this term is added in the denominator, it is loaded. So we can say this is sluggish compared to the interacting tank. And when you compare interacting tank and non-interacting tank, the response is sluggish in interacting because we have one more term in the denominator, which is the interaction term. So we'll see some more exercises in this. So take this picture. In this picture, we have one, two, three, four tanks, and then finally the tank output is with the pump. Okay. So we have to derive the transfer function between the level H and the inlet. So we'll follow the same fashion. Excuse me. So here tank 1. So inflow rate minus outflow rate. So Qi minus Q1, and then A1 into dH1 by dt. Then take Laplace transform, and then you can have like this. Okay, so which is Qi of s minus Q1 of s equal to A1 into this. The A1 into this one is tau 1 Q1 of s. So Qi of s equal to tau 1 Q1 of s plus Q1 of s. From this we have derived this one. Okay, so here we are not going to replace this q1 by h because we are concentrating on the final level, not this level. Okay, so right now you can just have q alone and the flow rate. Similarly, take tank 2, input is q1, output is q2, then take Laplace transform and have the expression as q2 by q1 because our concentration is on the final level, so you don't need to substitute the level for the outlet. Okay, so this is tank 2. Then tank 3 the same, Q2 minus Q3. From this we have this equation. And then for tank 4, be careful because it is pump. So Q3 minus A, and but my concentration is Q3. So this will be 0 if we take a Laplace transform. So here we have to replace this by H because our concentration is on that. Suppose if you concentrate only on the flow rate, means you can leave like this, Q3 alone. But since it is height, so this one. So finally we can combine this equation. How do we combine this? So if you multiply q1 by qi, q2 by q1, q3 by q2, h by q3, means we can cancel these terms. Finally you will get, in order to get this, you have to multiply all these transfer function. So this transfer function 1, this 2, and then this 3, and then this 4. If you multiply all this, you will get this transfer function. So like that we can do the transfer function. But if you have any resistance, then that resistance will be given over here. But since there is no resistance, so the numerator is just 1. Okay. So next case. So here we have given 3 tanks, but the values are given. The area of the first tank, area of the second tank, resistance offered by this valve here. Okay, resistance offered by this valve R2, R1 is given. Then this is the pump. Okay, so from this we have to find what is what is the transfer function of H1. This transfer function, this transfer function, and this transfer function, and you have to sketch the response for the same, and you have to find when the time is 3.46, what is H1 level, what is H2 level, what is H3 level. Okay, so in order to do that, first we have to derive the transfer function. Okay, so let us take the first tank. So we all from the previous expression itself we have derived q1 by qi equal to 1 by tau 1 s plus 1. And then since we need the h1 level, you have to replace q1 by h by r. So h1 of s by r1. So from this h1 of s q1 qi of s equal to r1 by tau 1 s plus 1. And then here they have given the magnitude as impulse signal. Impulse signal means like just like this. Only it occurs at particular time, that magnitude is 5. When you take Laplace transform, it is just 5 only. And then the resistance is 3.33. Then yes, then if you take inverse Laplace transform, this is the expression. So h1 of s equal to this, and then h1 of t equal to this. And then how do you plot the response? Simple. So take a take t, and then this is h1 of t. So start from the value 0, 1, 2, for example 5. So similarly, just substitute t over here and calculate the values and then plot. So this is t and then this is h1 of t. So suppose if you substitute 0, okay, e power 0 is 1, 16.65. So it starts from 16.65. Okay, and then for example, if you put infinity, e power minus infinity 0, so it start and then it moves somewhere and it is approaches unit infinity. So this is how the response is. So likewise, we can plot the tank response. Similarly, the second tank, same thing, Q2 by Q1 in the place of Q2 replaced by H2 by R. Then simplify this. Then since it has the influence of the previous tank, we have two uh, factors. So you have to apply this partial fraction which you have studied in earlier classes. So find the value. So I found A as this, B as this, then substitute that. So I will get when I got the response like this, H2 of t. So H1 of t is already done. This is H2 of t. Similarly, how do you plot the response? Same thing. Take t different values and then H2 of t start from 0 and infinity. But it takes a few values. So let us find out the response. If you put 0, so e power 0 is 1 and then this 0. So it is 0. When it is 0, the output is 0. Okay, so here this is t, this is h2 of t. So when t equal to 0, it starts from 0. Then infinity, if you substitute infinity, e power minus infinity is 0 and then this also 0. So it goes somewhere and it settles here. Okay. So in between the values, so you have to find and check the response. Okay, then H3 of t is exercise. It's easier for you, so you can try. And then one in the place of t, just substitute 3.46 and evaluate the response. So this is how we have to do this problem. Okay, then one more tank. So here two interacting tanks and one non-interacting to the interacting one. So we know that the transfer function for the interacting tank is this. Okay, we know this. So substitute the value and then we got the expression. And then for the third tank, again the same thing, that the same transfer function from step we have to apply. And then we found that this is the last term. Then you have to combine all the tanks. So H3 by Q2. So H3 by Q2 is R3 by tau 3s plus 1. H3 by Qi, if you want, we have to multiply these two. So multiply and then you will get this equation. And then the input is step 1. So if you take the Laplace transform, it becomes 1 by s. So substitute that. Then, so this is the equation. So you have to, because without converting into inverse Laplace transform, we can find out the initial value and the final value. Based on the initial value theorem, t tends to 0. So limit s tends to h3 of s. Okay. So the initial height is 0. Okay. Similarly, final value theorem is t tends to 0. Put s tends to 0 into s into h3 of s. Okay. So if you substitute that, we'll get. So your level varies from 0 to 2. So here this is t, this is final h3 of t. So it starts from 0 and it reaches 2. So in between the profile that you have to substitute. So how we have to split this, like a by s plus b by s plus 1, plus you have to simplify this. So c by that term, d by this. So find all a, b, c values and take inverse Laplace transform and plot it. But just to understand this, we can just apply initial value theorem and final value theorem. And then once we do this, we can verify the same with the MATLAB. Okay. So in the MATLAB, uh, okay, in the MATLAB, take, Simulink. In the Simulink, put the tank expression. This is H3 and then this is Qi. So take the tank expression and then here you give input step. Okay, then you can give the scope. And then click the simulation, you will get the response. So you can check the response with the same. Okay, so now we have learned what is liquid level, what is the dynamics. So just a recap on that. The liquid level system, this is the inflow, this is outflow. So we have derived the mathematical modeling as inflow rate minus outflow rate into rate of accumulation of that level. So this one, and then here the quantity is mass. Then I have clearly explained how to get this equation. And then to understand the dynamics, we need to know what is R and what is C. C is just area of the tank. R is H by Q. Okay. So this is the resistance. So based on this, we have derived the transfer function for a single tank, interacting tanks, non-interacting tanks. So compared to interacting and the non-interacting, interacting is more sluggish because you have one more term, that is the interacting term. Okay. So with this, we'll make a liquid control system. So this is, let me do for a single tank, but in this place you can have interacting tanks or non-interacting tanks. So first you have to give the inflow rate. The inflow rate is with the resistance. So this is Qi. And then here you have outflow, and then the here R2, then here you can say R1 resistance, and then this is here Q0, and then here is your level. Okay. So now just recollect the process control block diagram. So this is the system. Here you have to keep a sensor. This is level sensor. Suppose if you want to measure the flow, you have to keep a flow sensor or level sensor. So this level sensor information is compared with the set value, set point. Okay. This is the current value. This is plus and minus. This error is given to a controller. So this controller output is actuation, that is directly given to this. Okay. So based on the actuation, you can open the level, or you can increase the level, or increase the flow rate, or decrease the flow rate. Or either you can give a control actuator input to this or to this valve. So this is the complete liquid level control system. I hope you enjoy this session. So in the next session, we'll discuss the same concept, same mathematical concept for the temperature process. Okay, thank you. Thanks for watching.